Good morning, everybody, and thank you for joining us today for another Lighting Design Lab delivery. My name is Ramon Nobrainers, Technical Development Supervisor, and today we're going to be talking about Building Energy Code, the 2018 Energy Code when it comes to HVAC technology, alongside Duane, Jonlin, and Ben Roush. Next slide, please. So everyone should be pretty well accustomed to our rules here, but you'll notice everyone is muted. But please use the chat feature or the questions feature at the bottom right-hand side if you go to webinar dashboard. We will stop periodically to answer questions or comments. After the webinar, we're going to have very short surveys, seeing how we did, how the experience was. So please feel free to answer this and get back to us with that feedback. Also, a recording of this presentation, as well as the slide deck, is going to be posted on our Lighting Design Lab webpage. And if any additional questions or comments come up, please email us at lightingdesignlab@seattle.gov. I just want to call out that this is a collaboration between Lighting Design Lab and the Seattle Department of Construction and Inspections, all powered by City Light. And we're also being joined by Ben Roush again from FSI Engineers. So thank you for joining us, Ben. I think I'm gonna let you guys take it away. Yeah.
All right.
Hey, Ben, tell them who you are.
All right. Ben Roush, principal at FSI. A lot of letters after my name for a lot of different things, but what you really need to know, I'm a mechanical and fire protection engineer, sit on a bunch of committees, do a bunch of sustainable design, and really geek out on codes, which is why I enjoy presenting these with Duane.
And after so many lectures this year, everybody's probably tired of this slide, but that's me. I spent most of my career in private sector on big institutional projects mostly, and I'm coming up on a decade here with the city now running the energy code. And that little phrase in the bottom right there is where we should land 2 hours from now, which is we can do this. It's not an insurmountably difficult problem. And what we do have to do is we have legislation in place at the state and the city that are aggressively driving down our energy use and our greenhouse gas emissions for from the built environment, and we are taking all necessary steps to get there. So unlike most places where they're trying to argue about whether to do it at all, we're talking about how to do it. And with these 4 guiding principles that we used for the Seattle amendments, today we're really talking about numbers 2 and 3, that we're going to stop burning stuff in buildings to heat ourselves and our water, and we're also going to greatly reduce the amount of electric resistance we use so that we have our clean electricity left over for transportation and for moving the rest of the city off of fossil fuels. That bottom line here is the bottom line, that we're building things that can meet that 2050 target we saw before of carbon neutral operations without any major surgery to the buildings. So Ben, how do we get there?
Yeah, so I want to say we're going to break this discussion down into the code paths, and I'm going to do some terminology descriptions that we all have to agree on before we have these discussions. So prescriptive path, the just do it approach, the total building performance path, the energy modeling path, the target performance path, and outcome-based energy budget that's crossed out there are similar. There's an appendix that individual jurisdictions could adopt, but to our knowledge, no one has yet, except Seattle has the target performance path that's similar. And that sets a target that you must hit ahead of time. So engineering terms, pretty simple. Tea kettles, I like their avocado green one better, but tea kettles, electric resistance. They make heat by essentially heating an element. They have 100% of efficiency. The amount of heat you put in electricity, you get out in heat. So that's another way of saying coefficient of performance of 1. The refrigeration cycle uses compressor and things expanding and contracting, and we'll talk about it a little more at length. But the refrigeration cycle can easily have a COP of 3, and that's important because for 1 kilowatt input, you get 3 kilowatts of heat out. That's a way to think of that. So a lot of what we're going to be talking about here is heat pumps. We're talking about heat pumps because they use a third of the energy to accomplish the same amount of real work, meaning the heat. Heat pump layouts, y'all know these. Split systems in the center, just a regular PTAC. We're going to talk about those a little bit because they're not actually that great. And then VPACs, they're siblings. I think I got a couple more in here. Those were all single speed. The next slide is variable speed. There it goes. You know, so VRF-based systems, the little through-the-wall units by Epoca, inverter-driven compressors is a fancy way of saying variable speed. So you got split systems, VPACs, there's a whole bunch of form factors you can get those in. And you get a higher part load efficiency that way. They have, in a lot of cases, the full load running full blast isn't that much better. But the thing you really get, if you're using a single speed compressor, this is old knowledge in our industry that heat pumps won't work in this climate because it gets too cold, and then you got to use electric resistance backup, and can't do it. And for some of those single speed versions we showed you, particularly the PTAC I called out, the through wall, you know, sleeve unit, yes, particularly for Spokane, you're gonna need supplemental heat, and the PTAC will often cut off at 45 degrees and go to electric resistance. True. And that is for single speed compressors. That is still a truth in some of those cases. Let's go to the next slide. For variable speed compressors or inverter driven compressors, that's not true anymore. So if you look at the chart on the right, this is from Daikin, and it's just their VRF based system. And you can see in Spokane, you got to get the slightly extended temperature version, but it will retain near full capacity, well below what we would expect in Spokane. Seattle, you can get anything, and it's going to have full heating capacity without electric resistance backup. And this occurs also for inverter-driven compressors. Importantly, you can see the COP drops in heating mode, but it only drops to, you know, in Spokane, you're at 2.5. So you're still getting out 2.5 times more heat than the work you put in. I would take that any day over electric resistance.
And what's weird to me on that particular graph on the right is that from like -5 up to 30, there's really not much change in the COP.
Yeah.
And then it really takes off as you get into warmer temperatures, but it's pretty consistent down there.
It is, yeah, and the COP being up at the 4, 4.5, 5 at what we have temperature a lot of the time in Seattle, you know, it's not rare. If you look at our bin data, living in that 35, 40, 45, 50 range, we've got a lot of hours in that range. So there's an efficiency bump. This is specific to this Daikin system, but you do see more or less that trend. The warmer it gets, the more heat you can pull out of the air easier, and it tails off down to its limiting temperature, and that's really refrigerant based. So the refrigerant can only go so low before you stop being able to get heat.
So one principle we use in deciding what to focus on in code development is, you know, this pie chart. I once did a really great job of improving the regs for escalators, but what's that, like a tenth of a percent of our usage. So go for the big slices, which today includes that big chunk in red at the top and those green and blue ones down in the bottom. The other principle is that we need to restrict what we're doing to what is really necessary to get there to these goals, and to pick at any one point the most cost-effective methods that we have available. That last little bullet down there, I want to emphasize it's tough to quantify, but we've seen over and over again that as a new code provision kicks in and everybody starts doing things the new way, the incremental cost increase moderates, comes down.
I will
How
second
much does
that.
it cost?
My first interaction with the Seattle Energy Code was 2012, and there were some units that we couldn't even meet that efficiency. And then a year later, that was just what you could buy off the shelf. So it was no news. It just took a little while to catch up. Engineering view. So on cost, we got to be talking about this. If you're using electric resistance, electricity undoubtedly costs more per unit energy than gas. But again, you got that COP thing going for you. So it's really, you're going to use 3 times less energy. So this is again from Daikin, and take it with a grain of salt because it's for the country. Our power, our electricity is actually much cheaper. It should be even better for us. But you can see gas and electric, the yellow line and the green line, you're, depending on your outdoor air temp, you're living kind of like for like. And the warmer it gets out, again, we've got a bunch of hours living in that 40, 50 degree range where you're still heating, but it's moderate. You're actually more efficient to use electric. So that gas is cheaper paradigm doesn't really exist anymore, except when it gets very cold, and then it's still sort of like for like, as long as we're talking about heat pumps versus gas. And then we have to talk about who gets this savings. This is such an important concept. So when we talk about cost effectiveness, you start thinking about payback, simple payback or life cycle cost payback. And what really matters in those paybacks, if you're something like a residential building and you do something really amazing, but all of your tenants pay the power, you, the building owner who did this amazing thing, don't necessarily see that. But if you're a long-term property holder, there's things that most long-term property holders are going to do anyways because they're no-brainers. A lot of those things are in this code now. So as you see these things moving forward, think about this incentive structure and like raising the floor so that the person who doesn't get the savings still has to do some of the no-brainers.
So just wanted to mention about no-brainers. PTACs and PTHPs, it stands for package terminal air conditioner or heat pump. They become part of the wall assembly. You've seen these in all the cheap motels you've stayed in over the years, the ones that roar to life when they start running and then stop. They tend to have a U value as opposed to the 0.056 or something. They tend to have an insulating value of 0.5. So something on the order of 10 times more heat loss through them. And so even though this is a mechanical talk today, just be aware that our envelope requirements now require you to recognize and make up for the fact that you have a dramatically different amount of heat loss through those units. Another thing regarding the envelope to notice, and by the way, this must be a hell of a space. It's got 27 fans set up there to pressurize it. But with air barrier testing, we reduced the standard from the test standard from 0.40 to 0.25, which is what Corps of Engineers has used for a long time. But the big news is that now, whereas it used to be you had to just do the test, but you didn't have to pass, now you got to pass. And so we're saying that if you go over 0.40, the old standard, you got to keep retesting and fixing things until you do pass. The question I have in red bold there for all you mechanical engineers is now that we know that we have this much better air barrier, do your calculations actually account for that, or are they still assuming 1.0 CFM or something like that from the bad old days? Another thing
I can answer
go
that.
ahead.
The
All
simple
right.
answer is yes, they do. And LEED has gotten wise to this and is finally not letting us take credit for building a better building than baseline. It takes a pretty long justification for why our air leakage is better.
Excellent. We've continued to see people assuming that there's still bad leakage, even though it's being tested. I had made myself a project earlier this year to like make an overall chart of how the mechanical section in the code is organized, and basically I came up empty. These I think that over the years, everybody has simply dropped in mechanical requirements here and there isn't a real order. So you can paste this into the front of your code like I do to help find stuff, but can't help you with an organizing principle. But since we got an engineer on the call, he of course made us a flow chart.
Have to flow chart it. So when we're thinking about this, and this is a little preview for what we're about to talk about, the prescriptive path, you've got all of the things basically except C407 in chapter 4. And then based on your occupancy, you get kicked into doing a dedicated outside air system, DOAS, and TSPR, total system performance ratio, down in that bottom right corner. We're spelling out our terms. And again, we'll do all of this in more detail. But basically, if you flow chart this out based on your occupancy, based on whether you need DOAS and or TSPR, you end up with different requirements and different system minimums that you must meet. So it's something that you want to hire somebody who has worked in Washington State who knows this, so that you're not learning the learning curve with them.
Yeah, we have this problem when we get engineers from working from St. Louis or Kansas City or something, and they can't. It's really tough on people who've just seen this for the first time.
Yep. So big bullets. Mechanical efficiencies are almost completely unchanged, except if you go really dig in some of the IPLVs on chillers. We still don't have a way to rate heat pump chillers. We'll talk about that in a bit. Some mechanical controls changes, some DOAS clarifications about exactly when they're required and what it means. And then the total system performance ratio, which we'll talk about at length. And C407 is a complete overhaul. We'll also talk about that at length.
One little miscellaneous bit here is that for data centers, we in the last code we're using the 2016 version of ASHRAE 90.4, and we modified some values because they were just, I think, egregiously wrong. Now Seattle references the 2019 version of 90.4, and we don't have to modify things because they did just a really nice job of ironing out problems, and you have kind of a separate standard for large and small data centers, which recognizes the different efficiencies. Basic on 90.4.
Yeah, you might ask yourself, what is a large and small data center? What does it divide out as, and what's just a computer room? The magic line is 20 watts per square foot. So we have even small data rooms in office buildings that in some ways are going to meet that data center requirement. So it's a thing to be aware of as you get into it.
Yeah.
Hey guys, let's see if we can have a moment for a quick question, talking about code C403.2.3.3 of the 2015 Energy Code. It called out that it eliminated packaged electric heating, which assumed eliminated PTAC in new construction. However, 2018 now has HE PTAC allowed in all capacities. Just looking at it, see there was some incongruency there.
Yeah, you got to look at this as, so I understand what you're saying. There was a provision that started in 2015 that said you can't have electric heating if you already have DX cooling, that it needed to be a heat pump over a half a ton. It was a teeny capacity. Maybe it was 3/4 of a ton. And what you're saying now is wait a second, did you just go back on that? The answer is no. The intent is for these to be the packaged terminal heat pumps. But we all say PTAC is an industry, and I know that gets a little squishy. So if you go really big and you still have that requirement, you still need to be a heat pump over 6,000 or 9,000 BTH.
Yeah, and just be aware that you have to meet efficiencies at certain temperatures, which conventional heat pumps that just become a toaster oven, anything below about 42 degrees, are not allowed, and you have to account for the lousy insulation value of that through the wall unit. So we're moving people either to higher performing units if you're going to use a PTHP, or to find some better, more efficient, less wasteful system. They're kind of the very bottom of the barrel as far as quality of system goes.
And it's hard to find a better efficiency. Just put it out there.
TSPR, the total system performance ratio, is a backstop to make sure that when you put together an HVAC system, that the overall carbon emissions from your system is no worse than what we've defined as a pretty good system for that building type. And you have to do that in addition to complying with the whole HVAC system. By the way, this is sort of catching hold. There's very serious discussions going on at ASHRAE right now of adopting a version of this nationally. What's different about from between Seattle and the state is that at the state level, office, retail, library, education are required to do a TSPR. And Seattle has added multifamily and medical office buildings. And it's just basic, it's a simple ratio where a higher number is better, and you're comparing how much heating and cooling across the coils occurs to the amount of carbon emissions. There is online at PNNL a free calculation tool that will just step you through this. It's like a mini modeling, but instead of taking 5 days for a substantial building to do the modeling, it probably takes 3 or 4 hours.
Yeah, you end up doing basically zone models. It's quite easy. So these slides are from 1.5 years ago when we hadn't done any yet, and now we've actually done a good number of buildings. I can speak to a little more depth, but you know, this building, I made it up and I built it in a half an hour through the whole thing. It's menu based, it's quite fast. And like Duane said, this is way, way faster than a regular energy model, and it takes a bunch of assumptions into account, compares you against a theoretical baseline of the same geometry. Let's go next slide. So this is important as this concept. You have to convert your energy use to units of carbon because it's carbon based. So if you look at the comparative and you convert electric to therms, it's electric, that 0.7 line would be 20.5 pounds per therm. Or if you do it backwards, if you took natural gas, that 11.7 would be 0.4 pounds per kilowatt hour. And you might say, wait a second, gas is better than electric. And I'll show you in a bit why that is. But yes, that's actually true. And if you look at heat pumps, it's not true because you get 3 times less energy use. It's not one-to-one energy. Duane can go tell you lots and lots if you want to ask him the questions about how these were developed and the vast amount of discussion that went into that electricity factor, whereas we could all agree on most other things.
And whereas for this code cycle, we landed on that 0.7 pounds per kilowatt hour for electricity. Note that for the next code version that'll go into effect a couple of years from now, with some more sophisticated calculation, the state came up with 0.44, which ends up being very close to this number you see in the gas equivalent.
Mm-hmm. Let's go next slide. So the guesses on outcomes. So we don't have to guess anymore because we've done some. So what we can say definitively is the buildings that require DOAS anyways, which TSPR and DOAS have a very broad overlap. Every TSPR requires DOAS or high performance VAV. Those are gonna pass. Even if they're gas buildings, they're gonna pass almost every time. The only one we've had an issue on so far has been a retrofit where we're not touching the envelope. It's a bad envelope, bad, and it's close to passing because we are putting a DOAS system into an old building because of our occupancy. I can say this on that sample school that we did, that I showed you a little model on, electric resistance passed. Electric resistance plus DX cooling didn't pass. You wouldn't actually be able to do that in the code, but I wanted to see because the tool will let you do it. Change it to gas, doesn't pass. Change it to condensing gas, passes. Just that little tweak. And then of course your VRF, adding DOAS, things like that, those all just take it well over the line. And remember, it's carbon-based, not cost-based. So the more you do to reduce energy use overall, and heat pumps beat out gas every time, the better you are. So on CO2, how do we get that electric number? That 639 pounds per megawatt hour, that's a place to start with that. And like an engineer, I wanted to talk about where are we going with carbon. So hit the next slide. We got a couple of Senate bills that are passed. They are law, and it's going to take us to carbon neutrality in 2030 and carbon-free grid by 2045. So you can graph that pretty easily. You know, this is nothing magical. And I graphed that for gas. So the carbon emissions, I wanted natural gas for both regular 80% efficient and condensing 96% efficient. So that's those orange and gray lines. They get worse over their lifetime. Their lifetime's about 25 years. So great, they get worse. They use more gas per heat output. And then you replace them in 2045 and they start over. They keep getting worse again. The blue line is electric resistance, the flat blue line just below the gas. And then the electricity from the grid is that yellow line that goes down over time. And that's because we are legislatively required to decarbonize our grid over time. And then the heat pump's 3 times better than that already. So take this away. Electric resistance and gas are more or less the same, within a hand wave of each other for carbon right now, but electric resistance is going to get massively better and gas isn't. And heat pumps beat them all every time by a huge factor and are also going to get better over time. So that push for heat pumps on a carbon future basis, that's why you're seeing that.
So if boilers last for 25, 30 years, how long do heat pumps last?
It depends on the heat pump. So the cheap versions of single speed, you can expect 15 to 20 years. You know, the ASHRAE data has a, I guess you'd call it a wide bell curve. They say 15 years, but it has a pretty big bell curve on it, and it really depends on how cheap is cheap. Those PTACs that we keep deriding, or package terminal heat pumps, they're not going to last that long. You might be replacing them at 12 to 15 years. But the variable speed, the inverter-driven compressors, we have some manufacturers telling us to expect 20, 22 years. It's a pretty good system life out of a direct expansion device.
Cool. You've just been hearing about DOAS, dedicated outdoor air supply. That applies to office, education, retail, library, right? That in the current code has expanded now to include most assembly occupancies. It just worked, a DOAS system worked, a DOAS, shouldn't say DOAS system because the S is system, right? So, but your DOAS works well for assembly, and some of the exceptions that had been in the previous code that you got some freebies for using DOAS have gone away. And you see that last bullet point down there is that accessory occupancies, you know, something that's occupying less than 10% of your floor is exempted. So if you got a manufacturing plant and 5% of your floor area is in office, you don't have to do DOAS for that. And finally, just my definition of how a DOAS is different from conventional is just that the ventilation air is decoupled from the heating and cooling supply. You don't just use ventilation air for doing all your heating and cooling, and we require energy recovery from it. There's to be a little more clear about those assembly occupancies, you can see what is included here, and like in the A2, I especially want you to notice that A2 is mostly dining, restaurant things, and those were exempted because they're so process load dominated. But an A4 and A5 are like stadiums or something. But most assembly occupancies, as you think of lecture halls and exhibit halls and gyms and all that, are included in requiring DOAS.
So Duane asked me to speak to, are those different than B occupancies or other DOAS required things from the previous 2015 code. And the big difference is the amount of turn down, or from peak capacity with all those bodies in that space to that space is empty, but there's still a very nominal minimum ventilation rate you must meet. There's a vast difference in all of these assembly occupancies. And what that means is if we select the old school style giant fan sitting in a box, it doesn't have that level of turn down. It probably can't go low enough. And we're going to start talking more and more about things like fan walls, which architects are happy because they take less length of unit anyways. Fan arrays, they've got several names, system walls. And those have a capacity to turn way down because they're made of a bunch of small fans. And in the fanciest ones, they even have shut-off dampers so you can start turning off fans. We'll show you an example of that in a bit.
And I thought when I first saw this picture that it was somebody's exhibit of their gold and platinum records, but that's fan wall.
That's fan wall.
DOAS. So if you got DOAS, you need economizer anyway. If your chiller or heat pump is outdoors, or if it's in a space that has a wall or a roof adjacent to the outdoors. So if your only mechanical space is deep inside the building someplace, obviously getting that quantity of air in and out would be too much of a burden. But if you're next to a wall or a roof in your mechanical room, do a louver and start hauling air in. For DOAS plus demand control ventilation, in the Washington code, if you've got DOAS and DCV, you do not need energy recovery. In Seattle, if you do, if the space is larger than 650 square feet, so even a large conference room would need heat recovery. We just decided that was suitably useful. And in Seattle, if you've got 15 occupants or more per 1,000 square feet, according to the mechanical code, then you need this, and that just adds retail spaces mostly, and then there's a couple other really tiny occupancies. And finally, we said, yeah, 60% energy recovery is now easily achievable, so we have that instead of 50%. Okay, demystify us here.
Demystified. It's like the new catchword of the year. So I think it's really easy, really nice to have the graphics. Duane already showed you one that shows the decoupling of DOAS air and all of the other cooling air or conditioning air. So great. In a conventional system, back when VAV style or just a rooftop unit, you introduce outside air, return air, you mix it, you put it back into the space. Let's hit the next slide. So what we're saying when we say DOAS traditionally just decouples it, says great, I got outside air from a separate unit, then I have my space conditioning requirements. And it's important to make this distinction, the next slide, that we require in Washington State and Seattle codes that you also have heat recovery. So it's not DOAS, like many mechanical designers, particularly if they're out of state, are going to say, okay, you need a DOAS unit. I'm just going to get 100% outside air and shove it into that building. That doesn't meet the requirements. That's missing the heat recovery part. And that seems to be a very hard thing to explain to somebody who doesn't want to understand it. Next slide. So this is a unit, and it's got all of the parts we're talking about. So I'm going to point them out. That orange circular thing is heat recovery. That's an enthalpy wheel. The purple and yellow things that you see on both sides of that enthalpy wheel are respectively supply fans for the incoming air, the outside air fans, and the exhaust fans for the air leaving the building. And it moves over the two sides of that enthalpy wheel to move energy around. If you look above and below that orange circle, you've got little dampers that are giant like super skinny rectangles, that allows you to bypass the energy wheel and do an economizer function. On the DOAS side, there's also an economizer function on the space conditioning side to discuss. So you get true free cooling. But there are a handful of hours a year, maybe 50, where it makes a lot of sense to bypass that wheel. You're actually hurting yourself energy-wise instead of helping yourself. But again, it's a small handful of hours a year.
So, Ben, if say this is a big high school or something, what's the physical scale of that drawing we're looking at?
Yeah, so a lot of times you will divide up a building into wings and do a DOAS unit per wing. If I was doing a high school, I'd have a DOAS unit or two, per wing. Let's say it's 3 wings, and then those would be the size of an SUV, give or take. I have also done DOAS units for extremely large, I've commissioned them for extremely large buildings where it's, tall apartment building and they're actually doing the heat recovery, which was rare until the current code. And those can be built up, and those can be, the size of a bus, essentially, an extraordinarily large thing that goes on. It's not necessarily always a rectangle. They will bend corners and things. But
so those will come in, those more modest size units will come in on a crane in one lift, and
yep.
Those giant ones you're talking about would come in several chunks and get hooked together?
Correct. And if we're saying some office buildings we're doing, this just looks like another air handler. They can come down to tiny form factors. They make residential scale ones that are the size of a briefcase. So basically any scale you need can be done with DOAS.
Oh no, it's a psych chart.
You guys all remember psych charts, right? So we want to talk about effectiveness and efficiency. We have some manufacturers of heat recovery cores, and that can be, the core that only does heat recovery, or energy recovery cores that does latent and sensible, that want to give us efficiency. And that's really a theoretical maximum for that surface area and how much they actually gain. And that has nothing to do with what actually happens or what we care about. So effectiveness is the temperature delta between the incoming airstream and the outgoing airstream, and tells you how much heat, in this case, or on the next slide, enthalpy, so sensible and latent heat, or heat and humidity is another way to say that, you get. And so for Washington State, it's 50% energy recovery, 60% heat recovery. For Seattle, it's 60% heat recovery and 60% energy recovery. So basically, they leveled it up so that you kind of get the same amount of BTUs either way. And what that really means is that you're getting, if you have 70 going in one side and 50 coming out the other, you got 20 degrees, you want 60% of it, you're getting air back out that's usable at 62. That's what effectiveness means. It's a pretty simple ratio-based equation. If you have questions on that, we can pop these up at the end too.
Before we take a brief break here, Armando, are there questions coming up yet?
There are none. There was a person, I want to thank her, Carmen Cejudo, who shared the link to the TSPR, and I just shared it to the participants. But there are no additional questions. Thank you for checking.
We're doing okay on time now. So what should we give them, Ben? 3 minutes so you can get up, stretch your legs.
I go 4 minutes. That's enough time to make it to the bathroom and back.
Okay, y'all got 4 minutes. Go.
All right, I'm gonna mute it.
While we're on break, again, anyone with questions or comments, feel free to add them in the chat on the bottom right-hand side of the dashboard, and we'll be addressing them live.
Yeah, I got one that just occurred to me, Duane. When we talk about economizer, we mean free cooling, and that would typically mean on the, once we've divided systems, it would mean on the building system side, the room load side of the equation. And in old school systems, that would mean we open the outside air damper wide and we put 100% outside air in there for, again, free cooling. I put that in air quotes because you still got to run your fan. It's not totally free. And as I start thinking about that for rooms on outside walls, when you got a roof above you, right, we'll just use a rooftop air handler style with an economizer section, and it'll go all the way closed because we're doing ventilation in a different unit, and then it'll go all the way open, up to all the way open for economizer. If we're in a room unit, we got to do the same thing just with a wall louver, I guess. Yeah, I've been thinking about that form factor a little more because I'm having to do my first one.
Yeah, it's gonna take up some extra space to get through the wall, the big wall louver, and then you know, for your duct to transition down to what size it is that's going to go into your unit. So definitely worth taking a look at what the space constraints are.
Yeah.
All right. See you back in a few minutes. Okay, then, are we all refreshed and ready to trundle on forward here?
Feeling great.
So we added a table to the Seattle code that ASHRAE had just come up with, and that they were nice enough to give us special permission to add for heat pumps and heat recovery chillers. But this comes with a big asterisk that actually HRI hasn't really populated their list yet with manufacturers. But over the next couple of years, we will start to see units that are rated in this system, and this allows you to take advantage of a slightly more lenient efficiency load for heat recovery chillers. We wanted to make sure that we were allowing that rather than making you try to make those all their efficiencies work using the old tables. So we have a little bit of workaround that we put in there, but it's there for your use if you need it. Balanced ventilation, that unit you see there like works for a little apartment or something. It's drawing in fresh air and exhausting stale air and doing a good 60% job of heat recovery on the way. This is state code that you've got for dwelling and sleeping units. You gotta have mechanical air supply to each habitable room, and so we can no longer do apartments with trickle vents and just bathroom exhaust. It just doesn't work for you. So we put in a note there that HVI helped us with that says, okay, that's the Home Ventilating Institute, that how you can determine what the sensible heat recovery is from these, where if they're only publishing their the other system. So with that, Ben.
Yeah, so Duane asked a couple questions. I first want to say that, we did the first small teeny unit like this in a block house in 2011 in a teeny little dwelling unit. And you can get them as heat recovery, sensible, or energy recovery, sensible and latent. Again, same thing as the site chart. They're not that expensive. They're anywhere from $700 to about $2,000 for the unit, plus installation and ducting and whatnot. And they make, of course, larger units if you choose to do whole buildings. So Duane asked a couple questions. Individual HRVs, heat recovery ventilators in apartments. So our critique of that, or reminder about that, is, hey, you gotta change these filters at least every 6 months. They're teeny little filter media that they get clogged really easily. If you go to the large units with vertical shafts, like, yes, but you got those same things about fire dampers and floor area that you're taking up. And then doing floor by floor might be the sweet spot, because you don't necessarily need fire dampers depending on how you run it. And you certainly don't need the floor-to-floor fire dampers, but you're sharing a system that can transmit noise. So you got to be aware, unit to unit, do some noise baffling. But it might be the sweet spot of how you get this done in a residential unit for the least cost. And then we got to talk about energy impacts. When we get to do just simple payback analysis, this energy recovery has somewhere between a 4 to 6 year payback. If you do it on a life cycle cost basis, it can look even better over time. It's an obvious one of those no-brainers. But again, the person who gets to keep the savings is the person paying the power bill. And in most residential, that's the person living in the apartment, not the person who paid to build the building. So no-brainer, but without that code minimum, we're not going to do it.
And with those floor by floors, I was picturing that they would go in the ceiling at the ends of the corridors, and that might work out fine to just step down your ceiling several inches. Yep. Did you have a question, Armando?
Yes, guys, had a question calling out. To what extent is bypass of the heat recovery heat exchanger required by code?
So this is straight out of ASHRAE 62.1. So let's define that term first. In an energy recovery wheel, like that orange circle I showed you, that wheel is spinning. So you get that teeny little bit of air that carries over into that other side. And so ASHRAE 62.1 defines classes of air, and depending on what class of air you are allowed to have 10% or 5% bypass. So up to 10% can leak from the exhaust side, which is in residential, that's mostly restroom and kitchen, individual people's kitchen, not commercial kitchen. And it would be allowed to be 10%, and most manufacturers come nowhere close to that. They've got a couple percent. It's something we've been thinking about in a post-COVID world. Maybe we want to put a UV light in there also to be that extra level of protection, just to know that that little bit of bypass was not an issue.
Ben, there's another way to define the term bypass, and that would be that when they're correct outdoor temperature conditions, that instead of running your air through the energy recovery, you'd just bypass it straight to the outside or your incoming air. Does that?
Yeah. So those are those little dampers we were talking about, those teeny rectangles at the top and bottom of the core. The little units don't have them. Most residential units wouldn't have bypass dampers. And again, it's only a handful of hours a year where it would matter that they do or not. They would remain closed almost every hour of the year. So if that's what they meant by bypass, it's not an official requirement for residential.
All right. So space heating, the basic rule in the Seattle code is you got to not use electric resistance or fossil fuel as your main as your space heating system, which means, okay, do a heat pump. There's a long list of exceptions for, mostly for very small loads and for auxiliary heat in cold weather generally. But the one to look at for sure is dwelling units. We made it so that, okay, you can have 750 watts of electric resistance per room in an apartment, which for just about every apartment works just fine. And that bumps up to 1,000 watts for a corner room. So in apartment units where you're not going to do a heat pump, in order to supply summer cooling, you're allowed to have a nice wall unit or something like that. And there's a long list of other allowable electric resistance, but not other allowable fossil fuel heating. That just extends that list of exceptions. You can see that we're breaking down how much electric resistance you can have depending on the size of your air to water heat pumps. And then there's all those little ones, kitchen exhaust and heat tape systems and like that are exempted. Okay, but the engineer says.
It's pretty simple, Duane. Duane has it, except if you're going to do heating only, which we don't see a lot of people choosing that in our 100-degree summers anymore. That doesn't seem to be the greatest move for an apartment building. Still exists some of the time. But outside of those rare cases where you fall into those rules allowed specifically for apartments, you're going to use a heat pump. And these are some of the pictures I showed again. Split systems, inverter driven or single speed compressor, cheap VPACs, the slightly fancier than PTACs, the dual duct through the wall, Epoca, and now someone else I'm not going to remember is now making them. These are all systems we can use, and they got plenty of capacity. The only thing you got to watch out for is on those VPACs or PTACs is your electric capacity that cuts over at 45 degrees. You'll note on that exceptions, there are limits on how much electric capacity you can have. And that could be a limiting factor depending on your exact project situation and how much heat you need at low temperatures. And then the next slide.
By the way, before we go on, I should mention that I had a chance to talk to my counterpart in Lisbon, Portugal, and she was scoffing at our mentality. She says, all you people can talk about is heat pumps. And they have really warm days there in Lisbon a lot. And she said, we don't do any air conditioning in our social housing, and we carefully work to keep the direct sun off of windows, use a lot of thermal mass, and we're able to maintain comfortable temperatures. So it might be that heat pumps aren't the only answer to this.
Yeah, there's a cost impact to that. But if you go look at buildings from the early 1900s, pre-modern refrigeration era, they got the right idea. Operable windows that you open at night, big thermal masses that allow you to float the day. It goes great. And you know, dress codes that allow you to be comfortable up to 80 degrees. So if you're doing water side systems, not necessarily direct heat pump, you can use heat recovery chillers, which we talked about for efficiency a bit there. That's what's on the left. And then on the right is just your regular centrifugal chiller, but there's some great heat recovery potentials off of that if you go looking for them for your 4-pipe, you know, heating supply return, cooling supply return. There's some great heat recovery potential there. So putting heat pumps even in your central plant-based systems, if you're doing water side, still goes a long way towards it's what you can do to avoid gas.
We have made it clear that as opposed to conventional practice, we say you can't be heating out of the perimeter at the same time you're cooling in the interior of the same space at the same time. You'd think that would be so obvious, but as far as I can tell, mechanical engineers have always believed in a magical invisible barrier 15 feet in from the window wall that separated those two zones and kept them apart. But what we've said now is, no, you've got to like say it's the same space, and we've defined there how you determine, in case it's an odd-shaped space, what all qualifies as the same space. But you could have the perimeter in heating and the interior just neutral, or you could have the opposite. You could have the interior and cooling and the exterior neutral, but you can't be doing heating and cooling in the same space at the same time.
So I went and found a pretty picture of an open office that maybe is more than that 10% of floor area open, depends on what goes on there on the right. So that 10% opening is already pretty healthy that you're allowed to have, but if you can't have it, great. That said, with modern window wall systems, you might get a modest downdraft off of a giant sheet of glass, but we're about to talk about how it's going to be kind of hard to get more than 40% window area on buildings moving forward, even in energy modeling. And at 40% window area, if you do a little perimeter heater on the radiator, you have fantastic comfort. Even without that radiator, as long as you're doing adequate airflow and washing those windows well, you don't really need that simultaneous heating and cooling as long as you're moving air around a good bit. So modern design, yes, we still draw it that way, and a lot of engineers just do it out of habit, but we don't really need to do this anymore. And that's particularly true in these long, skinny form factors we're now doing to get better daylighting and views and other less energy tangible effects out of our building.
Yeah, and that is also helped by the fact that we have such air barrier tightness requirements that a lot of the draftiness has been taken away.
This is a lot of bullets, but all we're really saying is there's a bunch of changes in the ventilation and exhaust systems. Big ones to know: energy. There's a little bit of tweaked energy recovery ventilation. Kitchen hoods get a pretty good tweak. We'll talk about in the next slide. And you start having those same building isolation dampers you saw before, some occupancy sensors that didn't exist.
Hey, I had a quick question. If I missed from a slide or so ago, but you can share, what is the impact on efficiency if the filters are not cleaned regularly? You can get a rule of thumb on that.
Yeah. So filters are intended to be cleaned. Let's start with that premise. And in an adequately maintained building, what goes on is that filter ramps the fan over time if you have airflow measurement, or you get less air out of the same fan over time as you get dirtier and dirtier filters. So depending on that answer, the fan might use slightly more power with a dirty filter, particularly in the paradigm where you're trying to provide the continuous same amount of airflow and you're measuring that. So you're ramping the fan as the fan gets dirtier. It's a modest effect. We've tried building that into an energy model, and it turns out that's somewhat difficult. You just got to take an escalation on the fan power. But again, filters are intended to be changed, and there's a whole discussion on filters and COVID now, and you know, what is the right MERV rating? And we could go into that in the question and answer, but know that the higher the number, the higher the pressure drop, and the more power you use pushing through it. So there's a thing there to discuss. Okay, jumping back in. Hoods, kitchen hoods have very, very prescriptive CFM per linear foot of hood length that they are expected to meet. If you don't meet that, then you've got to justify why. And there are added hood controls, and heat recovery may be required depending on how you're doing. And heat recovery on kitchen hoods is not always straightforward for grease-laden, you know, air exhaust.
So fans, the industry is changing from this fan efficiency grade to this fan energy index, maddeningly similar acronyms, but we couldn't see enough products as we were doing this code to move away from FEG quite yet. And so in Seattle, we dealt with it. I spent some while working with industry by giving an alternate, so that if the fan you're getting only comes with an FEI rating and not an FEG rating, you can use the FEI instead, and that'll get us through, at least in Seattle. That will get us to allow you to use either one. If you're outside of Seattle, you might have to go and talk to your code official to make sure that they understand how this works, or just show them the Seattle amendment and see if they like that. Heat recovery, if you have buildings with 24/7 operations and with very large cooling systems, that condensate heat recovery that is going to be mandatory, and you put it into some kind of system where it will do some good, probably water heating. If you've got condensate from a steam system, you've got to take the heat off of that condensate water, and if you're water recovery anyway, refrigeration condenser heat. So grocery stores will have this huge amount of condenser heat that's useful, and now that a lot of grocery stores also have a deli and other things that use a lot of hot water, you got to take advantage of that. We're just trying to not throw away where we've got large amounts of what would otherwise be waste heat. Before I go on, Ben, did you have any comment on this one?
I am going to talk about it in 2 slides.
Okay, so heat recovery for space heating it is required if you have operating hours that are, say, longer than a traditional office building or school, and you've got large cooling towers and so forth. If you've got a DOAS, then that requirement goes away. You gotta take from your exhaust airflow. You've got to take heat recovery from at least 90% of that, and if you've got process heat, then you've also got to grab that additional heat. This is like heat that's already been created once and can be used again as low-grade heat for space heating.
Yeah. So Duane said, what would fall into this? You know, so you got to think didn't require DOAS already, which was all those occupancies, but is more than 70 hours a week, greater than 1500 MBH, 0.45 CFM per square foot, takes you beyond an office type space, which would have required DOAS anyways. So some hospitals, and many hospitals, are doing that water side heat recovery, putting that back into the airstream anyways. It was just a good energy savings. It made sense on a payback analysis. On refrigeration heat recovery for, particularly in the Pacific Northwest, for grocery stores. So you're cooling cases and then you're heating the space and you're paying at both sides of that energy. You might as well heat recover that and get some of that space heating back for free, or most of that space heating back for free, for what you're kind of overcooling with your case anyways. It's just good economics again. And then the data center, it's good money if you've got a use for that heat. And so we saw, what was that? The Amazon data center linked to, I don't remember, a big project McKinstry did, to link to a local hotel for their water heater and space heating needs. And it's basically, they buy heat as a utility from the Amazon data center. That's the extreme version of what we're talking about here, where you get that heat and you reuse it for space heating, because so much of the year we're in heating and it's low grade heat that's just sitting there waiting. It's good economics. We've done some oddball ones that don't necessarily fall in here, but you know, so like waste compressor heat off of transfer stations. Be looking in your buildings. There's these opportunities all over the place for low grade heat to reuse as space heating.
Okay, heating the great outdoors. If you have outdoor radiant heat that's not a portable device like I put in the picture here, but is built into the building, then if you've got any kind of outdoor heat, it's got to be radiant. We added something for unheated spaces like repair garages, or where you have an individual spot that needs some radiant heat to stay comfortable. In any case, would have to be automatic off by a timer or an occupancy sensor. And in Seattle, we add that's a 20-minute limit, that after which, you know, no motion has been observed, it'll turn itself off. And finally, I keep getting this from engineers, but there isn't anything called space heating for freeze protection in the code. You're either in a conditioned space or a semi-heated space or not. And another interesting thing, this is, I took this down in Oregon, Cannon Beach or something like that, you know, there was this restaurant, it was COVID, so nobody was allowed to be sitting outside together, and they had the fire pit blazing anyway. But these, it has to be manual on, so you turn on, it's got to turn off either after 1 hour maximum with a timer, or after 15 minutes if you're controlling it with an occupancy sensor. And then it's, you know, when people approach again, you can manually turn the thing back on. Here's C406 is where we ask every project, I say ask, you know, like we're polite, but we demand that actually every project have a certain number of things that are above code in there, and we give you points depending on which occupancy you are for that. So, and note that in Washington State, you have to get 6 credits, and in Seattle, you got to get 8 credits. I circled what's a school education, that additional HVAC performance efficiency, which I think is 10% better, gets you 2 of your 8 credits as an example. And also in Seattle, we just said, well, whatever you're doing, you can't get any credits for fossil fuel equipment. That last bullet down there, I've heard from a few different engineers and architects. It's like, don't leave this till late in the process. Get early on, decide what your credits are going to be, and then you can start working towards a whole integrated solution that's not going to cost you an arm and a leg. There's a DOAS for apartment building. I've highlighted there at the top. You know, you can get a couple of credits for it in Seattle, and whereas statewide you can get 4. But I wanted to reduce that to 0, but I was talked back off that ledge. But really, since you have to do the balanced ventilation for apartments, you've pretty much got a DOAS anyway, right? So you've got 2 credits pretty much automatically. And then if you look down at the bottom of that, just to finish that thought, you've got in the apartment building, you could get 5 credits for doing the high performance heat pump water heating, which would basically means that you've got you're using a very low global warming potential refrigerant, probably CO2, and that would get you to 7 credits. The lighting one is easy for apartment buildings, so that would get you to 8. You can, instead of DOAS, do this. Oh wait, no, I'm talking about a different one. This one is your C406.2. You can get at least 90% of your HVAC capacity if it's things that are in those tables that we have, and it's not gas. Oh, it's 15%, not 10. You got to be 15% better than the table value. It is, since equipment that does both heating and cooling, there's limits on things. You could say, okay, at least everything would be 5% minimum better than table values if the weighted efficiency was 15%. In the Washington Code, for some reason, we exempted heat pumps and heat recovery chillers, but not Seattle, because we got that table, and you can do it anyway. Also, big boilers are exempted in the state code, and I don't remember why, but we don't allow that in Seattle.
Yeah.
Dan.
I can say why. So what is hard to get to 15% or at least 5% minimum in capacity weight average? And the answer is oil-fired boilers, steam boilers, so large boilers have trouble getting over certain efficiencies. Even that 5% extra can be a challenge to find on the market. Some chillers have trouble meeting that 15% mark. Their ratings are already pretty good for what they can do, their theoretical maximum. So obviously, like Duane said, the heat pump chillers aren't rated yet and won't count for this. So you don't really have you've got a threshold to meet, but no rating from the manufacturer yet. So those just live on the side of the calc. Ground source VRF was an interesting one. As I was going through, I couldn't find ground source, so ground source VRF, really that's to say fluid cooled VRF or hydronic based VRF condensers that go to a ground source loop. I couldn't find something that beat that target by 15%. And then Duane also wanted me to answer, does the higher efficiency equipment cost more? And the short answer is yes, but it's such a nominal upcharge that in almost every case, it's got a less than 5-year payback, and any rational person would say yes to doing that nominal upcharge.
Okay, you've got to get C406 credit for tenant spaces in a shell and core building, and we made it clear this time that if you've got the shell and core HVAC systems built up, you can get credit for that same thing where you extend the system out to terminal units in your tenant space. And because we're we're all about trying to make this reasonable. So that's the language that I've highlighted there in yellow. Note that that last bullet down there, that if you're doing a shell and core building, the initial TIs can continue on using that same code edition that the building was permitted under for 18 months following the certificate of occupancy. So anytime in the first year and a half after you got your C of O, you can continue using that older code. After that, the stagecoach turns back into a pumpkin.
So as a schedule example, we're building a building permitted under the 2012 code. The certificate of occupancy will occur next spring. We'll have 18 months beyond that to permit under the 2012 code. This is a hypothetical because the 2012 code didn't have this version of C406. But you're given a pretty long window there, particularly for the long project timeline projects. So you do have to be aware of this as you move forward. When are your TIs going to be built out, and are you going to have a part occupied building when you hit that 18-month, what'd you say, Duane, pumpkin, coach turns into a pumpkin moment? And what are you going to do about that? There's a planning moment there that you and your architects and engineers should be talking about.
And sometimes it's difficult to plan, because I think I once saw that every time a new world's record tallest office building in the world has opened, it's opened into a massive recession, because it takes so long to build such a thing that by the time they finally got open, the boom was over. So there's a chance you could end up with a see-through building for a couple of years while you're waiting for the economy to recover.
Yeah, so it's super common in the core and shell world to install things like the VRF condensers, but not the VRF evaporators inside. And so you might run into an ugly there. The only other really ugly one we could think of was lab-based space, because you've got all those hoods and fans and all those things that weren't installed in the original that could actually knock you out of some of the C406 options. So it's just something you gotta do a little more planning for in advance.
This slide is just to reiterate what I've mentioned a couple of times, that you don't get C406 credit in Seattle for fossil fuel equipment, and that's under that DOAS thing and the HVAC systems and water heating. So the popularity contest here, it's a bit of an chart.
If you're gonna screenshot one slide, I think this should be the one. So we took, this is one engineer's view, but we took the, what do we think are the most likely to pursue to add up to 6 or 8 credits, and highlighted them in green, and we put the ones that we thought were less likely in red, and we left the ones in white that are meh, it's kind of project dependent. So Duane already highlighted those ones in red that, you know, this kind of makes sense for multifamily, and that those but they're really occupancy dependent. So you gotta look at how are you gonna add up to 6 or 8. And I was, I guess, outing my own self about that we've made it to 90% a couple times in this C406 paradigm where we're adding up to points instead of 2 credits. And we figured out that we didn't talk about it. We might be able to contribute a few of those points, but we didn't have that conversation as a design team, and we're going back to the drawing board. And so those were early days. We're putting that in our checklist now, but you want to process for that, for making sure that this is not a thing that gets missed. Particularly, I mean, if you put in a permit set with this, you would just be the laughing stock of the whole town.
Now, just to be clear, what you've got in red there does not mean those are bad. Those are just not quite as quick a payback as the ones in green. Is that right?
Correct. Or they don't fit into a lot of projects, or it's just we think you're going to want to take the bigger point totals to get your way there. It's not that you can't do the red ones. It's not that they're in some way not possible. They just have a longer payback or are more difficult in some of those occupancies.
Because like looking at the lighting one, that's the 20% reduction. especially as LEDs just continue getting better, more and more efficient over time, you might do really well looking at some of those.
Yeah, and right now it's a cost premium because it's such low lighting power density. If the code levelizes how it's dropped lighting power density over time, and it's occupancy dependent as well, yes, those points might become more lucrative.
So we've switched entirely our whole modeling procedure. The way we've done modeling before has gone into the recycle bin. We're now, the only allowable method is the ASHRAE Appendix G method. I show that guy holding a lump of coal to say that we've also switched from site energy to carbon emissions as how we're evaluating this. So Appendix G is comparing your design to what the emissions from that design to what it would have been if you designed to the 2004 ASHRAE 90.1. And that 04 was chosen as the baseline, which is supposed to stay the baseline forever, because it was the last time an energy code was ever straightforward enough that you could actually create a baseline. So this circle shows that at that state level, you can only use 54%, you can only create 54% as much emissions from your office building as would have happened in that ASHRAE 2004. Now, for Seattle, to compensate for the, or to align with the fact that we have made all these other prescriptive code changes that make Seattle buildings more efficient than elsewhere in the state, we've reduced that target by 10% across the board. So from that 54%, we've taken 5% off, and so now you're we've taken 0.5 off, which is 10%-ish of the 54, and so you'd have to hit a 0.49. You can see that the building performance factors there are all have the 10% knocked off of them, and to get there you use the carbon emissions factors in the table, which has been mentioned earlier. We came up with the 0.70 kilowatts per hour through a very non-scientific process, but it's what it is for this code cycle. 90.1.
So even if you knew about 90.1 for LEED, this isn't your grandpa's 90.1 anymore. The one used in B4 or B2009 was the 2007 version of 90.1. B4 was the 2010. So we're now talking about 90.1 2016. And what's important is that between 2013 and 2013 addendum, they threw the whole Appendix G up in the air and came up with that new method. Duane talked about it a little bit. There's that reference to a 2004 and then the building performance factor, which is a fancy way of saying how much better you need to be than your 2004 baseline. And so hypothetically, we will continue carrying a building performance factor forward that gets harder over time, gets a lower number over time. Let's hit the next slide. There's some ground rules we should cover first. So you cannot use solar PV to carbon buy your way out of this. You can only use that for 3% of the total carbon emissions. And the references to energy cost in Appendix G, because it's performance cost index, is going to be carbon for Washington and Seattle. And so you've got the emission factors. It's not that hard to do the math. I should clarify that it also took me an hour to do the math the first time before I built a spreadsheet to do it for me. So I'm really hoping there's a tool coming that does this for us instead of everyone building their own spreadsheet, and surely some of us will get math errors. The math works like this. It's pretty simple. Next slide, the PCI. So it's your building unregulated energy cost. That's to say the things that are like plug loads or process loads stays the same in both of the numerator and the denominator. And then the regulated energy loads, which is to say things like lighting and HVAC and all the things you kind of have control over as a designer, get multiplied by the building performance factor. So it's not everything in the building must be 58% better if you're multifamily, if you're taking that top line. Or let's do office because that's what I use elsewhere. So 56% better. It's only the things you have control over, which is the regulated energy use, must be 56% better. But the ratios start mattering when you really get into the math for unregulated and regulated energy use and what you show as a PCI target. And then your actual PCI, if we go to the next slide, your
Now,
actual
I have to correct Mr. Ben here that it's not 56% better. It's 56% as much emissions as the old one would have required.
Absolutely,
Really
thank you.
44%.
Yeah, 44% better. Yeah.
Yeah.
Yes, I need to do inverse math. Thank you. So you do that, you convert to carbon, and then off you go. And that doesn't seem crazy, except, and this is important, you have window percentages based on your occupancy for your baseline building. So if you're a grocery store, this is the worst one on the list. Now I guess warehouse is 6%. And it goes up towards, if you're not listed on the list, you get 40% window area on your building. So some of our buildings are going to get 40%. Great.
Multifamily in particular.
Multifamily is kind of the thing clearly not listed here. There will be a couple others as you get into it. And there is a C407 section that says your window area, you have to do that U factor times area trade-off, just like you did before. It's not a way to buy gobs o window by doing really good MEP systems anymore. So let's move on. How hard is this? So we have to start with the concept of a climate zone to have this discussion. How hard is this? How much improved over that 2010 or LEED baseline is this? And so we are really 3 climate zones in Washington. We're 4C maritime and 5B and 6B. And 6B for the purpose of the code is just honorary 5B. Will you hit the next slide for the map? And then we'll let that show for a second. So yellow, green, and blue, they're in Washington. Grand. And again, blue is just honorary green for that whole side of the state. So next slide, NREL has, or the PNNL has delightfully published factors for what they felt was equivalent for the 90.1 2010, which is sort of kind of the 2012 code cycle, and 90.1 2013, which is sort of kind of the 2015 code cycle. It's hand wavy, but stick with me. So you can see that in 4C and 5B, we got, let's do this office to office to office so that we're comparing apples to apples. And you'll see that by occupancy, it is not perfectly the same percentage every time. But office to office, you got 10% better from 2010 to 2013. That's sort of what we expect in a code cycle. That doesn't seem like such a big deal. And then if you go again, the next slide, to the 2016 version, it got, another 8% better for office. Again, not a giant jump for a code cycle. Let me put them all side by side for you there, the 2016 and then the Washington State Energy Code and Seattle Energy Code, which is the next slide. So great, 4C and 5B, oh wait, the code doesn't have climate zones like we talk about in 90.1. So you've just got a building performance factor for the state or for Seattle. And if we're sticking office to office, it's 0.58 or 0.61 for 5B to 0.56 for Washington State or 0.51 for Seattle Energy Code. So the Washington State Energy Code is modestly better, and the Seattle Energy Code is, like Duane said, 10% harder again, which is an actual performance increase of 5% on regulated energy use. So let me do some actual math for you on a real test bed. Let's hit the next slide. We have carried the Olympia City Hall. We did that under LEED v 2009, so ASHRAE 90.1 2007, and the 2009 energy codes. And we've carried this forward as a test bed because it's got a bunch of different office, it's got office and assembly and a police station tacked on. And it was a really good building when it was built. We got all of the energy model points in V2009. Compared to 2010 ASHRAE, it was 37% better. And it's gas heated. That's an important part of the carbon metric now that never mattered before this code cycle. Okay, next slide. So this shows how it has declining performance over time, but all it really means is that, every energy code cycle is harder. And so each energy code, it's performing slightly worse than the previous energy code. It's performing the same as a building. The energy code got harder, the floor raised. And we can't do this with the 2018. So I did just 2018, like using the prescriptive path. What would that building be? But we don't do that anymore. So next slide, we now do cost-based for LEED if we're doing the 2016 path, and we do carbon-based for Washington and Seattle. And go to the next slide one more time, and I'll highlight the right boxes. We, in our gas-based building, are highly performing back when. That is still modestly better than the code. It was still 20-something% better than the code. It's kind of almost passes the target. So on a carbon base, we have a PCI actual of 0.624, and the actual target for Washington was 0.66, or for Seattle was 0.622. So we were very close to passing. But this is an important takeaway. If you just model a baseline building on a PCI carbon basis, you get 0.83s, 0.85s, and that is this specific building with this specific gas use. If you made this a heat pump building, all of these answers would change. What this really means, if you take nothing else away, let's go to the next slide. If you take nothing else away, if an energy modeler gives you an answer with certainty forever after from now on, you should question if they really know what they're talking about, because it's so much of an it depends from here on. Occupancy, climate zone, unregulated versus regulated energy use, and your fuel makeup all go into this answer. And I don't know if I'll be able to ballpark this after I've seen 50 of them. But right now, I can't ballpark this. But let's talk about why would you do it? So we talked about, hey, this is new and different and kind of hard. We used to energy model mostly so we could have our glass towers of all glass windows by doing really good MEP systems to get more glass. And again, you can't do that anymore. You got a UA trade-off, and you might get yourself to 45 or 50% glass, but it's going to be hard to go beyond. And that UA trade-off path exists in the base code without doing the energy model if you do some other things like aspect your building correctly or advanced lighting controls or some other options. So the answer when I come down to it is I don't know why we're going to energy model any for code compliance from here on out unless LEED v4.1 uses that same 2016 baseline. So if I'm doing a LEED v4.1 project, I already have the numbers. I just have to convert them to carbon to show code compliance, and that'll be pretty neat. That's my main reason I think I'm going to use C407 from here on out.
Hey, Ben, it's Armando. I have a quick comment on the chat. Is there a tool that exists for the Seattle Energy Code similar or an adaptation of the ASHRAE 90.1 Appendix G compliance form? Does something like that exist for the Seattle Energy Code?
Yeah, and let's be clear, this is the Washington State Energy Code, and then Seattle has a harder building performance factor, but is otherwise essentially the same for this section. It doesn't exist, and what I'm looking for is for, gosh, who does the code forms? NEAA, is that right? NEEA?
No, it does exist. It's been made for us, and it's on oh Ben, what's the engine that the compliance form was built on.
Yeah, that's what I'm trying to come up with. The Northwest Code Council's,
But this was done for us by PNNL, and so it's on. We can send that out to people later. But that has been created for us with a Department of Energy grant.
That is really exciting. So news to me. Are you talking about You're not talking about ComCheck?
No.
Okay. I will look for that link as well. Exciting news.
Okay.
All right.
Were you done with that one, or did you have some more?
I'm good, unless other people have questions. That's a lot.
So you got to commission your HVAC system. It's amazing how much resistance I've had to commissioning in the past before it was required. But this is getting your money's worth out of all the investment in doing these fancy things that we're requiring, to just have somebody who's a disinterested party come in and see if it actually worked or if it actually does all the things that it's supposed to do. And it's amazing how frequently it doesn't. And so you can fix those, and then you're handing over a working system to people. So you got to have your commissioning professional qualifications to submit. You got to so if the person doing the commissioning works for the same company that designed or installed the system, you got to submit a conflict of interest statement that explains how you're going to still report any deficiencies to the owner that you find. We've got a checklist that you can fill out, and you've got to have a plan at the beginning that says what it is that you're doing and who's doing it. At the bottom there, we just mentioned that HVAC commissioning is required if your total system capacities are over that 240 or 300 kBTU.
That's a fancy way of saying 20 tons.
Thank you.
So when your mechanical person says 20 tons, that's your line. It's half as much as it used to be. Note on certified commissioning professional. I am one of those. There are a number of agencies that do this. If you're in commissioning and you're listening today and you haven't gone and done this, go do it. It was in the last code, not necessarily particularly strictly enforced. And I understand they're actually going to get questions on it this time. If you're an owner, ask to see the certification.
So next topic, metering, which I don't care about meters. There might be other kinds of gear you can get. What I care about is that there's this screen that the building manager can call up on, from a website, and they can see what the incoming energy was from the gas and the electric, and what they're seeing from the submeters for HVAC and water heating. In Seattle, now we all have also have submetering for lighting and plug loads and process. If you replace an HVAC system, well, we'll have some more discussion about that later, but there's also some metering required. But the essence is that if you'll start to be able to see patterns on a daily or weekly or seasonal basis, and if the building manager is paying attention, you'll be able to see an anomaly long before it becomes a serious problem.
So for the most advanced buildings we work on, we have in-depth energy meters on everything. But the code only requires that you energy meter by subtype. So you could put a meter on all of the lighting if you break out your panels correctly, and all of the plug loads, all of the HVAC. You don't have to have meters everywhere, although they are really helpful if you're trying to troubleshoot why I'm using more lighting power this year than I used last year. That's fantastic data for us data geeks who want to get deep into it and tune that building. But even at the holistic whole building level, you can compare this year to last year, or this temperature this time last year, did I still get that? And you will watch your building go out of tune. All buildings go out of tune over time. And you can decide what's too far out of tune to where I want to go retro commission and bring it back. Again, we see a lot, you can lay this out so that you only need a handful of meters, but we see so many systems that we commission that have, 30 and 40 meters because they aren't laid out well. It wasn't thought about at the beginning of the design, and then they just have to tack on meters everywhere. So if you think about this ahead of time, you can be really smart about how you do your electrical riser, and you can limit the cost of this system. Something to talk to your electrical engineer about.
Okay, as we're getting into what is our last 20 minutes or something, go through existing buildings. The general idea for an alteration is whatever was built legally in the past can stay that way pretty much forever. You can service things, you can repair things, replace filters, do stuff. But whenever you're putting in new equipment or new systems, and that includes replacing old systems with new systems, that new stuff has to meet code. And in Seattle, we have this much beloved concept called substantial alterations, where along with seismic and life safety upgrades, if you cross into this substantial alterations world, then the whole building has to come up to code, and we do give like a 10% break if you want to like make the envelope somewhat worse, or the overall building performance factor somewhat worse than would be required for a new building. The same thing that I'm talking about, substantial alterations, applies if you're going from an unheated to a heated space, or if you're changing from a funky occupancy like factory storage to something more polite like retail. If you're doing alterations, adding cooling to a space that didn't have it already, you've got to either do DOAS or some kind of economizer system. And if you're going to alter your existing cooling system, look at that very complicated table 503.4, where over the decades we've sort of decided what economizer work you have to do, or how you can make up for having no economizer if you want to do better efficiency instead. Sticky situations.
Yeah, you can thank our marketing director for this in the next image. So adding cooling, just tacking onto an existing system, pushes you into so many code requirements that it's not something that you just say, oh yeah, I'm just going to add some cooling. It's fine. It's going to trigger, like Duane said, possibly as far as envelope upgrades to do such a thing. You might be touching systems that don't have anything to do with cooling. And it also opens up a bunch of mechanical Pandora's box with those economizer provisions for, can you even meet that requirement in your particular building layout that was never intended to have cooling. So that's something to get deep into really early in design. If that's something you want to do, go talk to some mechanical engineers before you really get deep into it.
If with heating now, we're aligning with the new construction part of it, and we're saying either if you're doing substantial alterations or you're replacing the central HVAC system equipment or enlarging it, you got to meet that 403.1.4, which is the one that says no electric resistance or fossil fuel heating. The idea is that over time, Seattle existing buildings will get upgraded to heat pump systems, and we're aware that this is not popular, and it's often not cheap. We have one exception that says that if you got one piece of equipment that is failing, obviously there's no time to go hire Ben and start a design process and do that whole thing. You'd be having people shivering for months. So we're allowing one piece of equipment to be replaced in a like-for-like system. So we can get it through emergencies. But in general, when things are coming toward the end of the life, you got to start planning on switching to heat pump. Okay, there's the other sticky situation.
Yeah, there's your other sticky situation. So I want to reiterate what Duane just said a bit. If you have in Seattle and possibly in the next version of the Washington Code, depending on the next couple months, if you have a gas-based boiler, you will not be putting in a gas-based boiler again unless it's an emergency, like honest to goodness emergency. So a planned replacement won't count for that. So think 180-degree hot water up to steam, up to hotter than that. We have trouble with heat pumps getting there right now. And so if you're an old boiler system that wasn't designed to be condensing and at lower temperatures, you're gonna have a more major system upgrade than just that boiler. You're gonna have to at least address coils out in heat rejection equipment, wherever that is putting its heat out to, air handlers, radiators, whatever it is. We can't make steam with heat pumps right now. So there's a whole discussion about a major planned upgrade. And depending on what heat pump system you decide to go to, maybe it's not hydronic, maybe it's air side, and maybe it doesn't run down to super low temperatures and you need electric resistance backup, you may end up with you likely will end up with a higher electrical load on your building than you had previous to the upgrade. You know, chillers aside, it can trade off, but generally speaking, if you need electric resistance backup, it'll be a bigger electric load. So there's a whole discussion to get into with your MEP team, again, early, about what do we need and do I need to upgrade the building electrical service to meet this or not? Just it's all very much it depends. For building upgrades in existing buildings, I think we're going to be leaning pretty hard on VRF-based systems, variable refrigerant flow, you know, small pipes, lots of places, and pretty good efficiency. And then DOAS systems, smaller ducts probably than original air handling equipment if you had big air handlers built up. And that leads us perfectly into the next slide on refrigerant.
So refrigerant phase out, it's funny, when we gave this talk at the beginning of this year, it was still not really applying to heat pumps, but the legislature came back and said, no, wherever it says air conditioning or chillers, we mean heat pumps too. And so this is for HFCs, which is, or I should say for anything with global warming potential over 675, for things that are installed starting in 2025 in heat pumps, it's gotta be this lower global warming potential. And for equipment that uses that, this is when the equipment is manufactured and not when the building permit is happening. And so the equipment is usually manufactured a few months maybe before the actual install. And so I think that things that are going in for permit for larger buildings pretty much now are going to be governed by this new rule. So say goodbye to R410, R134, those are going away real soon.
So we've got 10 minutes left, right? I think I'm going to move real quick through refrigerant slides. So we did a really good job of getting our ozone depletion potential down with R410A, which is now really our industry standard. But the global warming potential is 1,890. And if you read other guides, up to 2,000 some over carbon dioxide. So it is short-lived, but very, very bad for global warming. Next slide. As we use refrigerants, we're making them into vapor, and then we're condensing them, and then we're evaporating them and making them vapor again. And that vapor leaks over time. almost every refrigerant system that exists out there, with the exception of some centrifugal chillers that some manufacturers will certify will never leak. Every single one of them leaks. And particularly with things like VRF, that can be a substantial quantity of refrigerant. That's why it matters. Next slide. Our ideal refrigerant, R410A, was pretty good. This is all weighted to R410A, so it's ratioed out. But R410A was really good, except that it has this high global warming potential. R32 lives in that greater than R410A, better COP, better performance, and better heat carrying capacity. And it's also slightly flammable. So our next version isn't currently code allowed in big enough systems. So that's looking at the VRFs of the world again with the big refrigerant volumes. You could hypothetically, with a gigantic leak, maybe build up to the lower flammability limit. We can talk about that if you want in questions. Let's keep moving. So CO2, that's an obvious one, right? Like CO2, you've seen that as a refrigerant, and we do see that in heat pump water heaters. There's several manufacturers that already make them. And it only really works in packaged equipment because it's freaking high pressure. It's not just high pressure, it's this purple line off to the left here that's way above everything else. So freaking high pressure. So you need super thick coils to make it work and a really robust compressor. So running those coils out in split systems, we're not going to do that in CO2, except in rare cases. Like there's one CO2 water heater that'll do it. Next slide.
Hey, Ben, I know that we're strapped on time, but I wanted to see if we can get a quick question in, and this is just something that's come a good amount of times before, but specifically with CO2 as a refrigerant, some of the conversation has been talking about how it's got less global warming potential than many of the other refrigerants. So more so the question is, why isn't it as a more ubiquitous refrigerant at this point in time, and what would it take to get there if it could be a good refrigerant of the future?
Yeah, so CO2 there, you can see it's got a global warming potential of 1. Everything's been indexed to CO2. And so R410A, that's your 2000 again, R22. So even going to R32, it's much worse than CO2. And CO2, again, must be a very, very high pressure for it to work. And that has a cost impact just because we need thicker coils, more robust compressors, higher pressure for everything. At that higher pressure, it's more likely to leak. You need, reasonably, like you need more robust fittings. It goes down the line. So it's largely a cost right now. That's why we're not doing CO2 as a refrigerant more often. And particularly in split systems, I'm not sure we ever will in any large scale capacity because we have to run such robust tubing. Let's hit the next slide. There you go. So refrigerants, what will equipment look like with different refrigerants? It will look exactly the same. It will be slightly different internals, but you may not be able to tell the difference looking at it like for like. If you had 2 units together, you might not be able to tell the difference. And this is not that big of a deal. As Duane said, manufacturers kind of have to play ball. Washington isn't in this one alone. California's doing it. I think, Duane, Virginia, I saw something. Other states are getting on board. So manufacturers are gonna play ball because they want to sell their equipment. It's going to be a minor headache in the near-term future as we design buildings that we already know need that equipment, and we start doing substitution requests, and it's going to be interesting. But just like R12 and R11 and then R22, keep going down the list of the Rs that are no longer allowed, it's just going to be another refrigerant we don't use anymore. It's another phase out. We've done this show twice in my career already.
So that gets us to the end of our presentation, but our friend Armando had a thing or two to say here. And there's our contact information on the slide, okay? Really appreciate all your time, and I hope the auditorium here is still full with people listening in. Armando.
Thank you very much, guys. No, yeah, we have the majority of the people still on the call, so thank you for hanging out with us. It's been a lot of information very quickly. Thank you for those who've submitted questions and comments. Wanted to bring up a couple of upcoming events from the Lighting Design Lab. In October, we're going to have another commercial heat pump water heating couple of sessions. We're going to go into a engineering deep dive as to the inner workings of heat pump water heaters, a little bit of the inner workings and a little bit of how we can implement them in engineering detail. So good information for those people who are looking at electrifying their water heating in their buildings, be it you're on the customer end or the implementation end. A good amount of information coming in October, and not here, but if it is pertaining to you in the lighting world, we're going to have a Light Fair post game show webinar November 9th. More info to come on that. Next slide, please. Seeing if the slide is going forward, but and just again, my contact info if you want any questions, comments, questions on recording and handouts, emails right there, mine and Duane's, and you can go to our website to get a copy of the recording and slides. To encourage if anyone has any final questions before we move on, but you can go to the next slide.
And note that this is the fourth of 4 sessions on code compliance, and those plus all the heat pump sessions we did earlier and the heat pump water heating. That's all happening on the Lighting Design Lab website.
Yeah, no, thank you very much. Good point, Duane. Even from earlier January and February, we had our code deliveries, again, with some of the same characters that we've seen here this month. And now that a couple of months have passed since code's been out, even though it's going to be, it's going to come into play in early 2022, but we've been able to be used to know the code for a good amount of the year, and we've done this series again now in August, September. So it's been very good, and thank you everyone for plugging in with us, and thank you for our speakers as well. There are no other questions or comments. One final thank you to everybody, and bid you adieu. That is all, folks.
Please take the survey.
Bye, everybody. Thank you, everybody.